Okay. So before starting on this, continuing with the lecture, couple of announcements. So I hope you have seen the announcements on Teams. The first assignment, as a first announcement, is that the current assignment on OS Lab has been modified. So now it is a 2-week assignment, and therefore a couple of more things have been added. So do check that out. And again, if you have any queries, then write in that corresponding channel where we discuss about labs. The second announcement is that we have declared the first class test of OS theory, which will be next Friday at this time. Right, so Friday 12th, Friday 19th will be the class test at this time, and the syllabus is whatever is covered till today. Okay, and we have given detailed instructions on how you need to take the class test. So it will be what is called a proctored exam. That means you are expected to have your video cameras on and write using pen and paper in front of the camera so that we can see you. Okay, so I hope you have seen these two announcements. Any queries about the class test specifically? So you'll have to write using pen and paper and then upload scan the answer scripts using your mobile phone probably, and then upload them to Moodle. And so the question paper that we will give will likely be of say 50 minutes duration. That other 10 minutes should be your time to upload the answers. But the whole thing has to be done within just 1 hour of 9 to 10. Just a query. So do you have classes just after 10 today, like Friday after 10? Do you have classes? Does any one of you have classes right after 10? Lab at 2 is fine, but right after 10 on Fridays. So just after this OS class, do any of you have other classes? Okay, fine. So I just note that, fine. Then, okay. Okay, the question is, Debojyoti ask? Sure. I mean, we just want a finally a PDF, etc. On to be submitted on Moodle. Whether you use your scanner at home or your mobile phone, that's, sure, if you have a scanner, it's up to you. So yeah, what you use to scan, we have no restrictions on that. Phone, scanner, everything can work. Okay, and again, so Shaumitra's question is, can we use laptop for seeing the question paper and scanning answer? Okay, as I said again, see our requirements we have specified. We have two requirements. One is that during the exam, we should be able to see you. Right? Second is we need a submission of your answer script in the formats that we said, like either as a JPEG files, every page, your zipped collection of JPEG files, or you put all the JPEG files in a PDF and send the PDF. These are our requirements. Now, how you use your laptop, how you use your mobile, if you have a scanner, whether you can use it, those things are up to you. We have no objections there. How exactly you will use your laptop, mobile, scanner? Our requirements are being able to see you while you give the exam and a submission in the correct format within the correct time. So there was a tip given, but that's just a tip. I mean, sure, if you have a scanner at home, definitely you feel free to use it. But our advice would be keep these things ready, because you have to complete the answering and giving, I mean uploading the answer script within that time. But it seems that none of you have a class right at 10, so I'll talk with Professor Mondal and sure, I mean it's okay. Any other queries about the class test? And of course, there is this announcement there also that kindly do not attempt to adopt any unfair means. It's an online semester, we know that. However, I mean, we have experiences of people trying to adopt unfair means in the previous semester. Kindly do not do that. We are very much particular about plagiarism and adoption of unfair means. We understand things like not everyone is equally bright. Some people might find things difficult, some people would find it easy. These things are okay. That's why grading is relative. So we understand those things, but yeah, yesterday some of you requested for more time in the lab assignment, so we have done that also. So in general, we are concerned about your well-being, etc. However, do not adopt unfair means. That is something which we will not consider at all. So in an online setting, of course, there are many different ways of adopting unfair means, but I would sincerely suggest don't do that. If you are caught, then we won't have any consideration. Okay, so let's resume the lecture. So we are discussing multi-threading, and we have generally discussed about threads and seen the pthreads library about how to create a thread. Then the pthread library gives us many options, like the parent thread may wait for the child threads or may not. So those options are given by the library. You are free to use, you are free to design the architecture of your program, like whether you want the parent process to wait for the child or not. Those things you can decide, but the library gives us the mechanisms. Okay, so yesterday we ended while discussing thread creation, and we understood that there is this issue about calling fork. So if a thread calls fork, what should be replicated? The whole process or only that thread? And we discussed about the couple of options. Let us start discussing today about thread cancellation. So what is thread cancellation? It's basically terminating a thread before it has completed. And this can happen due to many practical reasons. For example, suppose you are searching for something over a large database, and because the large database is large, using only one thread will make the search very slow. You want to speed that up, and therefore you are employing 5 different threads. Now suppose one thread has found the answer. Then there is no point in letting the other 4 threads also continue. So you would like to terminate those 4 threads before they have completed. So this kind of a termination of a thread before it completes is called thread cancellation. We have discussed yesterday how threads terminate on their own by calling some, like say if you are using the pthreads library, then there is a function called pthread exit. So that is how a thread will itself terminate. But here we are discussing about cancelling a thread midway, as in it has not terminated, we are cancelling it. I mean, so let's say the parent process is cancelling it, or some other thread is cancelling this thread. So that is what we are discussing now. And that thread which is to be cancelled is often referred to as the target thread. Now there are 2 types of thread cancellations. Asynchronous. First, let's discuss asynchronous cancellation. Here, some other thread immediately terminates the target thread. Okay, so this happens immediately. So at a certain point of time, some other thread calls some function to terminate this target thread. Now this can lead problem to in some situations. For example, let's say some resources have been allocated to the target thread. It has, freed up, it has allocated some dynamic memory, or it has opened up some files, etc. Now suddenly if that thread is terminated, then what will happen to these dynamically created memory or the open files, etc. So that can be one issue. Similarly, let's say the target thread was in the midst of updating data which it shares with other threads. And at that point, the thread was cancelled. Okay. So that can also lead to a problem. So here I have a question for all of you. How is this even possible? Like, see this line. So the target thread is in the midst of updating data shared with other threads. In the middle, it's cancelled. How is this even possible? Because right from the beginning of the semester, we have been talking about a uniprocessor system. So if this thread, the target thread, is updating data, that means that is one which is executing. So then how can some other thread cancel this thread? What exactly is going on? What is the situation that we are describing here? I hope my question is clear. That it seems from this slide that this target thread was updating data. That means most possibly it was running, otherwise it could not have been updating data possibly. So then how can some other thread cancel this target thread? Okay, Rashil says it might be doing disk IO operation. Okay. Pankaj says in other threads time quantum. Okay. Any other answers? Interrupt. Okay, no, we are not discussing interrupts here because again, interrupts will come from some outside system, as in interrupts are okay. Yeah, theoretically interrupts can be raised by your program also, like software interrupts. But then usually when we use the term interrupt, we usually mean something coming from outside, like the timer interrupts or some other device interrupts. But okay, again, so see. Okay, so what Vij is saying, let's say that other process can pass message to the first using global wires. But for all these things, the other process or other thread needs to run, right? So okay, let me say what is going on here. So the target thread is updating data, but this updation of this issue will come back later for us, and that is why I'm spending some time here, because we will. I mean, this is an issue that we have to understand. Okay, what is Akshat writing? Okay, so Akshat, sure. I mean, yeah, what you said is a possibility that actually the library is simulating the threads, but no, we are not talking about. So that's a possibility. That's a possible situation. Some library can be designed like that. But then when we are talking about say pthreads kind of library, we are not meaning any kind of simulation. So actually the threads are running. And as we discussed, some user level threads will be mapped to kernel level threads and so on. Right, so actually these threads are running. The library is not simulating them. So that's a plausible answer, but I mean, I mean, some thread library can be designed like that, but at least pthreads is not like that. Okay, so let me tell you what is happening, and this point is important to understand because it will come back in the next lecture, etc. So this updation of data, this is not a single operation. So possibly let's say this thread is updating a large array. maybe some elements of that array has been updated. At that point, this thread can be swept out of the CPU. And that can happen due to an interrupt, etc., etc. But then understand that this updation of data is not a single operation. Updation of data can happen over many time quantums. As I said, maybe a large array has to be updated. Some part of the array was updated in this time quantum. Then the process was swapped out, or the thread was swapped out. Again, when this thread run, it will update the next few elements of that array and so on. But now let's say that it had updated half of the array, then it was swapped out normally, like an interrupt came, etc., etc. But at the time when it was out of the CPU, maybe it was sitting in the ready queue, some other thread cancelled it. So some other thread ran, and that thread cancelled it. Then comes a problem, because that array has been only half modified or half updated, and this thread is now cancelled. So what will happen to the other half of the array? Okay, is the situation clear? So don't think that this is happening together, as in it cannot happen that, say, again, in an uniprocessor system, which we are discussing, it cannot happen that one thread is updating a data structure and another thread right at that point cancels it. It's not possible. But as I said, the updation may happen over many time quantum. So that's the situation we are discussing here. And this is an important situation, which again, in the next couple of lectures, we will face this situation many times. Okay, so I hope this is clear. So yeah, these can be some problems with asynchronous cancellation, where the cancellation happens immediately. And so therefore, so what would you think intuitively? What would be a better alternative? Since these problems are there in asynchronous, intuitively, what do you think there should be another option for? Okay, in the interest of time, let me proceed. So the other, yeah, something like what Pankaj said. Okay. Okay, what Rahul said is also an option, but that's a difficult option. Create a new thread for doing the rest of the task. I mean, then the thread which has cancelled the target thread needs to know that the target thread was in the midst of such an operation, and therefore a new thread has to be created. That's a difficult operation. Rather, what Pankaj is saying, that is closer to the what happens. So, and let's see that option. It's called deferred cancellation. So some other thread indicates that a target thread has to be terminated. But this is just an indication. It is not immediately cancelling the target thread. It's just informing or notifying the target thread that you need to terminate. The target thread periodically checks whether it should terminate. And if so, then it does the housekeeping. That means possibly it completes all updation of data structures, etc. that it was doing, and then terminates itself in orderly fashion at a suitable point of time. So here the cancellation is not immediate. It's deferred. So some other thread simply indicates or notifies the target thread that you should end. The target thread periodically checks whether it should terminate, and then it terminates at a suitable point of time. Okay. So let's see actually what happens with pthreads. So in the pthreads library, threads are allowed to choose one of several cancellation modes. Again, I'm not going into details, but you may look it up, like what kind of cancellation modes pthread allows. The textbook Galvin has a good discussion on this. Now, also the pthread library allows threads to disable or enable cancellation. Right, so a particular thread cannot be cancelled if the cancellation is disabled. So a particular thread is allowed to declare that I am, for some time, let's say, disabling cancellation because possibly I'm going to start an important operation. And while I am doing this operation, I should not be cancelled. Or before I complete this operation, I should not be cancelled. So it allows a thread to disable cancellation. However, suppose one thread has disabled cancellation, but some other thread indicated that, okay, let's say some particular thread T has disabled cancellation, but some other thread X still indicated or notified T that you should terminate. Then this cancellation request will remain pending so that this thread T, after it has completed this operation, can later enable cancellation and respond to the request. Okay, so it allows that a particular thread will say that, okay, I'm going to start an important operation, so I want to disable cancellation for some time. So if any cancellation request comes within this time, then it will, that request will be stored. After this thread finishes its important operation, it can check whether there are any cancellation requests for me. If yes, then it can choose to terminate itself. So understand something here. Here we are talking about threads within a particular process. And therefore, you have written the program. So the threads are cooperating with each other. So you can say that, oh, one thread is trying to cancel another and that thread does not want to be cancelled. Sure. But then you as a programmer should have taken care of these. Like you should have written your program in such a way that this thread, before starting an important operation, will disable cancellation. And after completing that operation, will again enable cancellation or check whether it should terminate and so on. So pthreads by default, they provide the deferred cancellation. And asynchronous cancellation is not recommended because of the problems that we discussed 5 minutes back. So basically cancellation occurs only when a thread reaches a cancellation point. And what is that? How to establish a cancellation point? By calling this function, pthread test cancel. So if a thread calls this function, it means it is wanting to check if there is any pending cancellation request for it. If so, then maybe it will do something and then cancel itself or terminate itself. So exactly this is what is usually done. It checks that this thread checks if a cancellation request is pending. If so, a function known as a cleanup handler is invoked. So the cleanup handler may do things like releasing dynamically allocated memory or closing any files that this thread has opened, etc., etc. And then this thread can terminate itself. So that's a cleaner way of a thread termination compared to simply one thread cancelling another immediately. Okay. Okay, and how to raise this cancellation request? Like one thread wants to notify another thread that you should terminate yourself. So for that, the pthread cancel function is used. And it is passed an argument that TID, this is the target thread. Like you have to indicate, one thread has to, when calling this function, indicates which other thread it wants to cancel or terminate. The important part is that calling this function indicates only a request to cancel the target thread. It does not mean that TID, the thread TID will be immediately cancelled. Just a request for its termination will be lodged. How exactly this target thread will terminate depends on how that thread is programmed. And it's how the target thread is set up to handle the request. Okay, so again, when you are writing the program, you should have handled this, that you should have written the code in such a way that your thread checks if there is a cancellation request. like using the mechanism we discussed in the previous slide. This one by pthread test cancel. And then you should have written the program in such a way that it terminates cleanly, as in it does not have any partially updated data structures or dynamically allocated memory which it did not free. These things should not happen. This, as a programmer, you should take care. The pthread library gives us these mechanisms. Like one mechanism is to initiate a request for terminating another thread. And for that target thread, it gives a mechanism to check if a termination request is pending, and then do some cleanup. Okay. Now, so this business of terminating a thread, etc., this happens through a mechanism called a signal. And that is what we will discuss next, because signals are an important concept in OS. So at this point, any question about thread cancellation? Okay, if not, then I proceed with signal handling. Okay, so what is a signal? Signals is used in a Unix system to notify a process that a particular event has occurred. Okay, it's a mechanism, you might say, which is used to notify a process that a particular event has occurred. Now there are two types of signals, synchronous and asynchronous. The difference is as this. A synchronous signal is usually generated by some invalid operation, such as say, illegal memory access or division by zero. So basically this asynchronous signal is delivered to the same process that performed the operation that caused the signal. Right. So let's say that your process was developed, your process was sent a signal. This is most probably because your process did something illegal, like an illegal memory access or division by zero. In contrast, asynchronous signal may be generated by an event external to the running process. The process which receives the signal. So here, in case of an asynchronous signal, your process may get a signal by some external event. Say because a user has terminated the process, or a timer has expired, and so on. Okay, so there are these two types of signals, synchronous signal and asynchronous signals. So we will discuss more about signals, sure, but at this point, any question? I'm expecting a question here. That is why I am asking. I'm expecting a intuitive question here. Excellent. That is the question I was expecting, which Rashil has asked. So how are these signals different from interrupts? Because it seems you are telling that both of these seem to be delivered to a process in order to notify of some event. Like we also discussed about timer interrupts, which is basically, informing that the time quantum has expired and so on. Okay, so yeah, so let's answer, and maybe some of the other comments or questions that were asked may be clarified by our discussion itself. So let's proceed. So yeah, so that's a natural question to ask. Are signals and interrupts similar? The answer is not exactly. So what's the difference? Okay, so again, Pankaj's question, let's discuss this. I think these questions will be answered. So yeah, interrupts and signals are not quite similar. So what's the difference? These. So interrupts are used for communication between the CPU and OS kernel mainly, whereas signals are used for communication between the OS kernel and other processes. So signal is more of a software thing, whereas when we hear the term interrupt, we usually associate some hardware with it. Theoretically, there is something called a software interrupt also, right? Like when you do a system call, sometimes an interrupt can happen, but then primarily when we use the word interrupt, we usually have a hardware connotation in mind, like some hardware has, some device has generated an interrupt. And that interrupt usually comes to the CPU first, and then the CPU hands it over to the kernel because the interrupt service routine in the kernel has to be run. Right, so the interrupt is usually initiated by the CPU or some device, or yes, some instructions can also lead to a software interrupt. But most commonly interrupts happen due to some physical device wanting to say something to the CPU. Right, so yeah. Whereas in a signal is more of a software concept. So it is initiated by the kernel or by some other process and given to another process. So the kernel wants to tell your process that maybe you have divided by 0. So that's basically a kernel telling your process. And how are the interrupts managed? Well, eventually it is managed. The interrupts are managed by the CPU, where the current task has to be interrupted or swept out, and the kernel provided ISR has to be invoked. Right. So this we discussed earlier. Like somehow the CPU must know where the ISR for this interrupt is. And we discussed of some tables called interrupt vector tables, etc. by which the CPU will know that if an interrupt has come, which routine to start running. Right. So that usually that routine is interrupt service routine in the kernel. Whereas a signal is eventually managed by the kernel, which delivers them to the target process or thread. Okay, so yeah, I can understand there might be some points of confusion, so I would suggest you to read up some other material. But in general, signals and interrupts are not the same. Intuitively, the primary difference is that when we use the term interrupt, we have some hardware in mind. Again, I'm having this disclaimer that software interrupts are also there. However, usually, normally, like unless your program is raising an interrupt or something like that, a software interrupt, usually the interrupt happens because some device, some physical device wants to inform the CPU of something. Like the timer wants to inform that the time quantum has passed, or some IO device wants to inform that IO operation is completed. Then those devices raise interrupts. And they are managed by the CPU, which must run some kernel routine, which is called interrupt service routine. But a signal is more of a software phenomena. Like the kernel wants to inform your process, or one process wants to inform another process of something. So for those things, signals are used. Okay. Okay, so now we are discussing signals. So now I have a question. So I think all of you have at some point of time used Control C to terminate a process. Now this happens by a signal or interrupt. Okay, this slide gives the answer. The question was not quite framed well. So basically this happens through a signal. A particular signal called SIGINT is generated. And this indicates to the process that you should be terminated because the user has possibly asked for you to be terminated. Okay. So there are many signals defined in POSIX. So again, remember POSIX is a standard for compatibility between operating systems, etc. So POSIX defines many kinds of signals. If you look up the internet, you will get a comprehensive list of all signals on POSIX. So here are some written, like SIG abort is for abort, and SIG ill is for illegal instruction. SIG int is what we discussed, for a user has interrupted this process. SIG seg v. So this is what, like a segmentation fault kind of thing, an invalid memory reference. Okay. So the kernel can tell your process that your process has made an illegal memory reference. It has tried to access a memory location which was not in its address space. So then your process will typically get 6 segv, this signal from the kernel. Okay. So of course, now the important question is how is a signal handled? So as I said, suppose your program has done a division by 0, or your program has done a like illegal memory access. So then kernel sends a 6 segv signal to your process. So then what will happen? How will the signal be handled? So how a signal is processed is as follows. It is generated by the occurrence of a particular event. Like let's say your program accessed an illegal memory location. So the signal will be delivered to your process. Possibly the kernel will send the signal and the signal will be delivered to your process. And then the signal has to be handled by a handler function. We call this a signal handler. Now there are two types of handlers. One is a default handler that the kernel runs when handling the signal, or a user defined or process defined handler, which is used to override the default handler. So let me ask, suppose your program has performed an illegal memory access. What do you think the default handler will do? So if your program has done a illegal memory access, what do you think the default handler will do? I'm sure all of you have faced this. I mean, you might not have known about signals and all that you are knowing now, but I'm sure you have faced this situation. Exactly. The process will be killed. So by default, if your program has done an illegal memory access, then you know a segmentation fault happens and your process is killed. Okay. So basically the mechanism is that a 6 segv is delivered to your process by the kernel, and the default action is to kill the process. However, if suppose you are writing, it's possible that you write a program where you want to catch a signal and then do something. It is possible. So the mechanism is provided that you can define your own handler to override the default handler. Right. So suppose you want to actually catch that signal and do something which is not the default action. I mean, some situations can arise like that. So then that's that mechanism is given. Okay. So let's see. Okay. So that is about signal handling. So usually a handler is written, etc. We will see a very small, a simple signal handler soon in the next couple of slides. Okay, so yeah, just a minute. Okay, let me go there. Yeah, so let's write a small signal handler. Okay, So for that, see, we have hash included signal.h. This is the header file which defines different kinds of signals. By the way, I hope you know you can actually read header files. Like you can figure out where the header file is in your memory and then sorry in your file system and you can read it. Like it will possibly be under /user/include something like that. So you can read see what the signals are defined, etc. But okay, so this is the signal handler function. Void because it should not return anything. Signal handler int signal number. So basically this 6xv sigint, these are all some ultimately defined to some integers by signal.h. So here this is your signal handler function. So this is what you want to do. Like if signal number is sigint, then printf received sigint. Okay, and this is the statement by which you are registering this function as a signal handler. So the signal, this call is saying that you want to register this function sig handler as a handler for sigint. So now if your process gets a sigint, then the default action will not happen. Rather, this function will be called. Okay. Fine. So you can so feel free to explore this. You can write other. I mean, you can. This is how you write a small signal handler. As in, you write a function where maybe it's quite possible that even if your function, even if your process has to terminate, you want to do some cleanup before that. So then you can do this. You can register a signal handler inside that function. You do your cleanup, and then you can terminate. Okay. So yeah. So this is how to write a signal handler. Now, yeah. Okay, and so this is about handling the signal. Okay. However, the other story of this other side of the story is suppose your process wants to send a signal to another process. So how to do it? Right, the previous one was your process has received a signal, then how can you handle it? Now I'm talking about the other side. Your process wants to send a signal to another process. What to do? For that, if you use a like a C code, then you can use this function kill. So kill will send this signal to this process. Okay, kill will send this signal to this process. Of course, just I'm not going into that much details, but just understand that this does not mean that your process can kill any other process in the system. I'm not implying that. Okay. So just because let's say you send a kill to the init process, that does not mean that the init process will be killed. You have to have that privilege, or you have to have the right to kill a process. Only then that process will be killed. Like a process also has a owner kind of thing. So yeah, I mean those things are there. But yeah, suppose it's a process created by you only. You own that process. Then you can, from another process, you can send a signal to that process. Okay. Also, even via the shell. Okay, even via the shell, you can send this kind of a signal. So kill minus signal number, then process ID. Okay, this if you send that also will deliver a signal to this process, which is PID. Okay, so yeah, fine. Okay. Okay. So now, fine. So that is about signals, how to handle a signal, how to send a signal to another process, etc. Now, signals have nothing to do specifically with threads. Like signals can be sent to processors, threads, etc. Both. I mean, signals can be sent to processors as well as threads. However, so this slide, what it describes is to send a signal to a process. Okay, so I'm writing CPID, sending a signal to a process. But now, what about the thread counterpart? Like, can you send a signal to a thread, etc.? Or what happens when a thread receives a signal? Let's discuss that a bit. So, for single threaded processes, handling signal is kind of easy because the signal will be delivered to the process. And then either the default action will happen, or if that process has registered a signal handler, then that signal handler will run. Okay, so it's relatively simple for a single threaded process. But for a multi-threaded programs, there are additional complexities. Suppose there is a multi-threaded program which has got a signal, let's say from kernel or from some other process. So to which thread should this signal be delivered? Now there are several options, some of which are written in this slide. The signal can be delivered to every thread in the process. The signal can be delivered to some particular threads, or a specific thread can be assigned to receive all signals on behalf of this process. Right, so you can do that also, that you register a specific thread saying that all signals sent to this process should be sent to this signal. So that thread. So that thread is specifically for handling signals, while other threads do other jobs. Also, to which thread a signal is delivered may depend on the type of the signal. So let's say a synchronous signal. Remember, a synchronous signal we discussed, usually this signal happens because of some action by that process or thread itself. So let's say some particular thread has done an illegal operation. Then the synchronous signal should be delivered to that thread itself. You should not possibly stop other threads because one thread did something illegal. However, some asynchronous signals such as SIGINT should be sent to all threads. Because suppose you are running a multi-threaded program and you have pressed Ctrl+C. That means you want the whole process to end. So this SIGINT should be sent to all threads in the process. Right. So typically you understand that for multi-threaded programs, whom to send the signal, etc., has an additional level of complexity. But yes, signals exist both for, signals can be sent both to one process, one thread, etc. Okay. Okay. So, yeah. And as I said, this is how to send a signal to a specific process. Okay. Now, how to send signal to a specific thread of the same process? Again, the pthread library gives this function. So you can first of all, one thread can send a signal to another thread of the same process. Like as I said, you just cannot send a signal to any process, any thread in the system. A signal can be sent to another thread of the same process using this function. And see, now we are telling the thread ID to which this signal should be given and what signal to give. So int signal. So here int signal, you can give numbers like 0, 1, 2, but the standard procedure is to give the name of the signal like SIGINT or SIGSAGB. And all these are mapped to some integer that you can figure out from the signal.h file, header file. Okay, if you want to know more about signals, then there are lots of, resources. So one good site, one good place to start is the man page. Right, so if you do man signal, then you will get to know a lot of signal. I sincerely hope that you have developed the habit of going through man pages. If not, do that. Man pages give a lot of authoritative information about many different concepts, functions, system calls, and so on. And like if you are on a Windows system, etc., then the whole man is actually replicated on the web. Right, so if you also just do a Google search saying man signal, you will be directed to the man page, which is also on the web. And man pages are so important that the whole man pages are replicated on the web. Okay. So yeah. Now, okay. So that is more or less what I wanted to cover today, but I have a couple of things more to say. There are a few more slides here, which I am not going through now, but it's left for self-study because of a reason. That material will not make sense now. It's called thread mutex. But yeah, I mean, for that, I mean, this part will make sense after we have covered the next topic, which is process synchronization. Right, and this is, so process synchronization we will see specifically will refer to that discussion which we had today. That what is happening, that one process is being cancelled. So okay, we were discussing this in the context of threads, but similar situation can happen because of processes. I mean, for processes also, that one process terminating another or one thread terminating another while it is in the midst of updating an operation. What is going on? Like, how can that even happen? So that is what we discussed, that it is possible that this updation is happening distributed over various time quantums. So it is possible that a thread or a process has done half of its job, but then it can get, I mean, then some other thread starts to run. Okay. So suppose like this, that there are say, two threads or two processes, both of which are accessing the same large shared array. Now, suppose one thread is updating the array, another thread is reading from it. So let's say that the array is large. It takes several time quantums to update the whole array. Now, let's say the updation thread, let's call it the updation. Okay, let's call it the process. Okay, updation process and reading process. So the updation process ran for some time. It updated part of the array, not the whole thing, but then it got swapped out. Now at this point, if the scheduler assigns the CPU to the reading thread, and that thread, when it reads the array, it will get an like invalid kind of array contents, because some of the locations have been updated, some of the locations have not been updated. I hope you understand the problem. The updation thread was updating the array. After doing a part, it was swapped out. Again, when it will be allocated the CPU at some later point of time, it will update the rest of the array. But before it could complete, it was swapped out. Now, if the reading process is allocated the CPU, it will get an invalid state of the array, where some elements have been updated, some other elements have not been updated. And that can lead to bad situations. I mean, this is an invalid state. I mean, nothing should be done with that state of the array. So we might want to have a mechanism where the reading thread will be made to wait until the whole updation is completed. So we might want to write processes like this, that the updation process before starting the updation will do something which will prevent the reading process from accessing the array until the whole array has been updated. So this is called process synchronization. Similarly, there is a concept of thread synchronization. So this part I'm not covering right now. After we cover process synchronization, I would suggest you read this part. I mean, the next few slides. I'll give you the slides. Feel free to look at it. But then the next few slides, the next, I think 3 slides or 4 slides will make sense only when the next topic is covered, like process synchronization. Okay. Okay. And okay. Now just give me a couple of minutes. I just want to try a couple of things. I don't know if it will work, but just to give you a feel. For that, let me open up a browser. Okay, so I have opened up a Mozilla browser. Fine. I mean, I can just go. Yeah. Okay, so I have opened up a Mozilla browser. Fine. And also let me open up a shell, a terminal. So first of all, can you see both the browser, the shell, etc.? Okay. So now, first of all, you might like to see what are the different processes running in your system. How to see that? Any idea? Okay, Sriyash, I'll come to your question, but let me just let me just try out this for a couple of minutes. Yeah, so suppose you want to figure out what processes are running in your system, how to do that? Yes, Rashil has given the answer. PS is a command which shows you the processes, running in your system. Yeah, top is also one, sure. But so fine. Let's do a PS. Okay, sorry. Yeah. So see, all these are processes running on the system. And see again, I hope you can see. So these numbers that you see, say 1, 2, 3, 4, 1, 2, 3, 5, etc. These are the process IDs. Like every process has a process ID. Okay. And you can see a lot of statistics like when the process started, maybe how much time it took, how much time it has run, etc. Let's just do one thing. Let's see. Yeah, okay. See. Okay. So I have done a psaux pipe head. Head is a command which is used to read the top 10 lines of something like a file or something. So I have used ps or ux and then I have redirected the output through a pipe to head. So head is showing me the top 10 lines. So see, you can see now you can see the headings. User, PID, percentage CPU, percentage mem, and so on. So all these are statistics being maintained by the kernel that how much CPU percentage is this process using, how much memory percentage is this process using, and so on. What command has been actually used to run the process and so on. So as you see, the first few processes, in fact, much more than 10. Okay, by the way, and this column here, user, this is the owner of the process, like who started it. Remember I said during the class today, you cannot kill any process. You have to own that process to kill it. Right. So all these processes which you are seeing now, these are owned by the root, which is who is the super user. So you as a normal user cannot simply kill process PID1 because you don't own that process. Right. And see the process with PID1. This is the process about which I have told you in some earlier classes. This is the init process, the first process which starts running. You see here, init. Okay, so this is the init process. However, there are many processes. So all these processes are being run by the root. However, I guess there are many processes which I am running. Let's see. Let's see. Yeah. See now what I did. Okay. Okay. I did this. So in the PS output, I am now searching for sghosh. What is this grep? GREP? What is grep? Yeah, grep is a very strong pattern search engine. Okay. grep is a very strong pattern search engine or pattern search machine. Pattern search tool which uses different kinds of regexes and so on. So basically what I am doing is in the output of PS, I am looking for my own username because I want to figure out what processes I am running. Okay. So see, these are the processes which I am running. Some of them, there are lots, but these are the processes which I am running. You can see the The owner here is S Ghosh. And see, these processes also have IDs like 2431, 2446, etc. So I hope you understand the initial processes are usually owned by the root because those are the kind of kernel processes, the init process, etc. But later on, the different user processes are also running. So these are the processes which I am running. Right. Now, let's see. Specifically, I want to point out, look at this process. Firefox. So possibly it's this window which I just started. 5 minutes back, I started this Firefox window. Most probably, I'm not sure, but most probably, so you can see several processes because again, Firefox, when you start Firefox, actually several processes start running. And see, again, you can see this. Okay, so you can see all these processes have Firefox. But then somehow I feel this is the main process. Why do you think? Again, I'm not sure. I mean, I do not know so much details about Firefox that I can tell you exactly what I'm saying is correct. But intuitively, it seems that is the first process. Why? Why do you think I'm guessing this? Okay, good point from Shomnath. First PID among Firefox processes. Anything else? Yeah, so Rashid also says the same thing, PID order. So typically PIDs are assigned sequentially, as in first must, I mean, it's not possible that, um, I mean, so when the kernel is assigning process IDs, it will do it in a typically increasing order. So 3299 must have started before 3363, 3401, etc. So that's one reason. That's a good point that this must be the parent process. Also, if you notice, the other processes are having a child ID. Okay, the other four processes are having a child ID, which also some of you have mentioned. Right. So most possibly, this is the parent ID, this 3299, and this has started these child processes. Intuitively, again, I admit that I do not know so much about Mozilla Firefox, exactly that how it runs, etc., etc. But just from this output of PS, it seems that this is the case. Okay. So now you want to do an experiment, which may fail because I do not know exactly the details of Firefox, but just I want to see. Can I send a signal to this process and close it? This Firefox. Okay. So I'll go back to this slide. This is what I'm trying to do. From the shell, can I send a signal to the Firefox process and kill it? Okay. So I must send a suitable signal to process ID 3299, or what was it? Yeah, I must send a suitable signal process. Sorry, I should send a suitable signal to this process 3299. And what process, what signal to send? Yes, Rashil has pointed out. Actually, it's kill -9. -9 is what is it? SIGINT. I forgot. Yeah, I also, yeah, so just like Rashil, I also remember the number 9. But yeah, what signal actually it is that I forgot. Okay, let me just do a search. SIGINT, yeah, quite possible, but just let me search. Signal 9. SIGKILL. Okay, not SIGINT, but SIGKILL. Yeah, that's what I thought. I mean, yeah, these are, I mean, again, no one remembers all these details. As I said, you can easily look up these things in the internet. But yeah, kill -9 sends a SIGKILL, not SIGINT. Okay. Okay, so let's try that. So I want to send a signal to process 3299, the SIGKILL signal. So I'll write kill -9 3299. Okay. Now I'll think this experiment to be successful if just after I press enter, this Firefox window closes. Okay, let's see if it happens. So I hope we can see the Firefox window also. Now let's see if it closes. Okay, so I'm going to press the enter. See, it closed. Right. So from the terminal, I sent a signal to this process and I killed it or closed it. So this is about sending signals. It's just a small demo about sending signals. So now you can understand what this slide means. So this is what I'm talking about. From the shell, I just showed you that first of all, I demonstrated the different processes running and stuff like those. And then I showed you how to send a signal to a process. This particular one, we decided to kill the process because that has a visible effect. But of course, you can send some other signals to a process also. There are lots of different signals. Okay. Okay, fine. Yeah, so I think there was one question. Yeah, so Srihash asked, is it correct to say that a signal is always generated by the kernel in response to a hardware interrupt? No, you cannot generalize in that way. I mean, sure, it can happen in certain cases, but it's not always. I mean, yeah, I'm not sure if it happens always due to a hardware interrupt. Okay. I mean, this I'll have to check, but sure, it can happen that due to a hardware interrupt, a signal was generated. But whether it always happens like that, I'm not sure. I can think of other situations where even even without some hardware interrupt, a signal was could be generated. Actually, see this one, which we just demonstrated. I don't think I raised any hardware interrupt. I used the shell to send a signal. I'm sure that signal was delivered by the kernel to that Mozilla Firefox process, which closed it. So I don't think that hardware interrupt is a necessity for the kernel to send a signal to a process. Okay. But yeah, I am not, I mean, I can't say I'm completely sure, but intuitively it seems it's so. Yeah, so Srihash, technically isn't that a keyboard interrupt first though? I'm not sure. I don't think so. I don't think so. That what I did, I don't think that I generated a keyboard interrupt. Because again, see, SIGINT and SIGKILL are not the same. SIGINT is the one which I think generates, results from a keyboard interrupt. But SIGKILL, which I sent, is not the same. Okay, Rachel says, can root user kill PID1? Well, I guess I have not tried that, because that will completely shut down the system. But I guess you can. Actually, there is something called init level. So like if you actually want to, how do you shut down your system, a Linux system? Of course, you can use the GUI. You can, I mean, what we normally do, but there is something also else. You can actually, there is a command called init. Okay. Yeah, so shutdown is a command, right? Also, there is a command called init, and init gives a run level. Like you can actually look these up. As I said, develop the habit of looking up man pages. Like let's say man init. So yeah, init. Okay, man pages are often difficult to understand. So I'm not trying to even read the whole man page. Okay. I just wanted to figure out the init level. Okay, let's leave it. But okay, let us try on one other thing. The shutdown. I think shutdown internally will be linked to init, but I might be mistaken. Let's see. Okay, shutdown is used to halt, power off, or reboot the machine, right? That's fine. But does it have any relation with init? That is what I wanted to see. Okay, no, okay, maybe not. I find. Okay, then yeah, maybe shutdown is also another separate command. But anyway, init also can be used. Like if you do init 0, init blank 0. So you do an init command with run level 0, then the system will shut down. So yeah, but coming back to Rashal's question, I'm not sure if this is the same. This will have the same effect, but I'm not sure if this is the same as killing PID1 or killing the init process. But of course, ultimately, if you do init 0, then ultimately the init process will also be killed because the system will shut down. Okay. Okay then. Yeah, I took quite a bit longer today, but I just wanted to maybe demo like so these things which we are discussing. Actually, you can try it out. So yeah, using I mean this, you can check the process status and different processes running on your system. You can even start your process, your own process, and then check how processes are behaving and so on. Okay, so feel free to do these experiments. Fine. So I'll stop this class today. We'll continue next week. Thank you.